We will begin this video by discussing how images can be processed and how objects can be classified. Images are composed of different color gradients which can be represented by pixel values. Different objects can exist within the image as a subset of its space. Objects are not only represented by their pixel values, but some features that lie therein, horizontally and vertically. But what if we attempted representation by utilizing many non-parallel segments of the object? This could hypothetically reduce the amount of information being passed into a neural network and reduce the workload. But how do we generate these segments, and how are these segments related? To do this, we can begin by taking the discrete derivative of the pixel values. This is a simple heuristic for finding edges. Where these edges exist along the x and y axis can be thought of as a point of interest. The middle of all these points is the center of the object. To reduce redundant information, we can condition these points to be some distance away from each other. This can be done by dividing the space into segments, radiating out from the center of the object, the size of which is determined by some theta j. This introduces a new hyperparameter which is intrinsically linked to the number of points selected. Now that the points are selected, we can create the line segments we desire. 2 points are selected. Then, a ray is created facing the direction from one point to the other. As the ray increases in size, points are sampled along the ray. The values for these pixels and its derivative make up the features of this segment. These can be thought of as the colors and textures, respectively. These features could be utilized to create a message passing matrix. But how? To answer this question, we need to take a look at the dataset and determine if the decision rules rely on nonlinear or linear transformations of the features. The dataset is fully synthetic, consisting of some objects that are rotated around with different sizes and lighting. By producing many segments and taking the aggregate for the brightness and the texture, we can generate a 2D scatter plot. These scatter plots can show us the expressivity and the overlap of these aggregated features. When a convex hull is placed around the clusters of these features, it is easy to see how they interact in 2D space. A heat map can be generated showing the intersection space and the unique space of each label. Both the heat map and the visualization show us that there is intersection between these features. We can speculate then that the message passing matrix should be determined by some nonlinear transformation of the features. In this case, a multi-layered perceptron is used to extract more features from the two that we provide. This means that the data for the texture and the brightness needs to be aggregated. We can use the mean to do this. By passing this data into the MLP, we receive the message passing matrix. These matrices are used to inform the nodal features through each pass of the graphical neural network. We could utilize a simple method of connecting a node to the farthest unconnected node to create our graph. This is based on the idea that these edges could represent the surface of the object. As a whole, we take our dataset, create the graphs, and pass them into the MLP. Each layer performs its message passing to calculate the node features. These nodal features are aggregated together, and a linear transformation layer is used to classify. So, how well does this perform? With a training set of 2,700 images, the model performs amicably. The end result is about a 93% test accuracy. This can be compared with a 4-layer ResNet, which has an accuracy of 100%. However, this is not the only metric that can be used to contrast between the two. The ResNet is over 40 times the size of the GNN, though the ResNet has not been pruned. They also have similar computation times, though the GNN takes a while to set up the graph. It's important to note, however, that this process is unoptimized. There were further explorations surrounding this project. However, there is one I would like to address. What happens when you add more labels? Of course, the model performs worse. What's interesting, however, is utilizing the principal component analysis within RBF kernel to look at our previously aggregated data. We can see that there is a suggested correlation between the confusion matrix and the separability space created by the PCA. This informs us that there probably needs to be an increase in complexity for the model, which suggests that there still is a lot to explore.